All right, everybody. One last one on page 11, and then we'll get into page 12. So, draw 3 cards without replacement. What is the probability that the first 2 are kings and the last is a queen? Okay, let's keep using probability notation. What's the probability that I get the first 2 to be kings? So a king, and then a queen. And this is without replacement. It's very important that you know whether or not you're putting the card back in the deck each time you calculate these probabilities. More and statements means I'm multiplying. I'm going to multiply these probabilities, but I understand that if I'm not using replacement, that's changing the probability as I go. So the first time I pull a card from the deck, I want the probability of getting a king. We're going to work on this guy first. Okay, well, the probability of getting a king out of 52 cards, 4 of those are kings. So this first guy right here, the probability of doing that is 4 out of 52. And so I'm going to multiply by the probability of getting this next king. Now, I'm not using replacement, so there is 1 less card in the deck and 1 less king, as a matter of fact. So now there's only 51 cards in the deck, and only 3 of those left are kings. Okay, only 3 of the kings are left in the deck, because again, 1 was plucked out. And then lastly, we got another and statement. I'm going to multiply. I want the probability of selecting this queen. Okay, well, how many cards are in the deck now? We started with 52, and I pulled 2 cards out, right? So now I've only got 50 cards left in my deck. How many queens are available in the deck? We haven't taken out any queens, so there should still be 4 queens left in the deck. Okay. So if you were to multiply this out or get a decimal, this is going to come out to 0.00036. Or in other words, if you were to draw 3 cards without replacement, the chance that they would go king, king, queen would be 0.036% chance that would occur. Okay, on to page 12. All right. We looked at this table earlier. Again, somewhere back in a couple videos ago, we looked at this contingency table where we had 1,000 subjects take a drug test. You had some people that use drugs, some people that do not use drugs. You had people test positive for using drugs and test negative for using drugs. And if you recall, there were terms like true positive, false positive, true negative, and false negative, and true negative. Remember, the positive just means they tested positive. The true or false means was it accurate, or was it correct, or was it not correct. So those that tested positive for drugs and used drugs, that's a true positive. Whereas these guys that tested positive for drugs but do not use drugs, that was a false positive. Okay, so same set of data. They're just going to ask us some different types of probability with them. So it says if 2 of the 1,000 test subjects are randomly selected, find the probability that they both had false positive test results. Okay, now this could be a little tricky because they don't actually say that you're using replacement or not using replacement. But you can kind of figure it out from the wording here. Just think about what would happen. They take 2 of the 1,000 people that were randomly selected. Okay, so if they were doing this, they were sampling 2 people. It's not like they would take 1 person out of the 1,000, say, okay, where do you fall on this table? And then say, okay, now you go back in the population with everyone else because I might pick you again. No, what they're doing is they're taking 2 people out, and so that's without replacement. Once 1 person has been removed, now there's no longer 1,000 people to choose from the second go around. There's only 999 people. Okay, so the question is, find the probability that those 2 people both had false positives. So that means they tested positive, but it was incorrect, okay, because they are not a drug user. So the probability of a false positive and another false positive Again, this is without replacement, not using replacement. Okay. The way I need to multiply these, then technically the rule would be the probability of getting a false positive. That's for the first person. And for the second person, it's the probability of getting a false positive, given that I've already plucked someone out of that population that has a false positive. Well, the probability of getting a false positive test result, out of the 1,000 people that were surveyed, 90 of them gave a false positive. So 90 out of 1,000. Okay, now when you go to grab that second person, again, you've already pulled one of these people, one of these false positive people has been pulled out of the population now. So now the probability of getting another false positive test result, well, now there's only 999 people to choose from, because again, one's been plucked out. And furthermore, the one we took out was a false positive test result. So instead of having 90 of them left, one is gone. There's only 89 of those things left. Okay. I'm hoping this is making sense, guys. Please watch these as many times as you need. I think the ideal thing is watch them ahead of time before class, so when we have our virtual class, we can do extra examples. You can ask questions. You know, that's the time to work out all the kinks. Sorry we can't do it right now. Anyways, if you multiplied this out or got a decimal, you get 0.008. Okay. So they ask here, is it likely is it likely to randomly select two subjects and get that they are both false positives? Well, here was the probability of selecting two folks and having them both be false positive. Right? So would we consider that likely, or would it be considered unlikely? It's definitely low probability. If you move the decimal over, this is, no, what are you doing? This is 0.8%. Remember, our cutoff is 5%, so it's well below 5%. The probability is 0.8%, below 5%, thus very unlikely. Whoops. Okay. Remember, 5% is our threshold, our cutoff. So here it says, find the probability that two randomly selected subjects both have a negative test result. Okay, so here I want the probability of getting a negative test result and a negative test result. I'm going to take two people out of the population here, and I want the probability that they're both negative. Again, this is another case where I'm not using replacement. It doesn't say that. It's without replacement. But if you just think of how this is going, again, it's not like they're pulling one person out, one of the 1,000, saying, did you get a positive, negative test result? And then say, okay, now go back in the group. Because we might pick them again, right? So this is being used without replacement because they haven't indicated any otherwise. And generally, I think that's our good default. I guess it depends on the problem, but that's a good default, is to be safe. Assume they're not using replacement unless they specify they are. But anyways, this is the probability of getting a negative test result first, times, because it's an and statement, getting another test result that's negative, given that we already pulled one out that's negative. Oh boy. You don't have to write out this rule. I'm just kind of trying to stay consistent with my work. So the probability of getting a negative test result, let's do that first. Where are the negative results? Those are all the negative results, 866 of them. Okay, so 866 out of 1,000. That's the probability of getting a first negative test result. But then if I'm looking for another negative test result and I didn't put that person back in the population, Now there's no longer 1,000 people to choose from. There's only 999 people to choose from. And there's no longer 866 negative test results. There's one less than that because, again, I plucked one out. There's only 865 negative test results. If you multiply those out, you get 0.7498, about 75%. To get, if you were to take 2 people out of the population, the probability that they would both have negative test results. Now that doesn't mean they do or don't use drugs, because you could be negative and still use drugs. That's just the probability of getting 2 negative test results if you pull out 2 people. Okay, and lastly, find the probability that a randomly selected person has a positive result given that they are not a drug user. So I want the probability of a positive result given they are not drug user. Again, don't go looking for the formula for this. Just think of shrinking down your sample space. They're not a drug user. If they're not a drug user, that means we're talking about these people right here. Those are the people we're talking about. Those are the drug users. Let's try the non-drug users. Those are the people we're talking about, okay? They are not using drugs. So from that batch of people, the non-drug users, what's the probability of getting someone that tests positive? Well, of that group, which 860 and 90, that's 950 total people, 90 of them had a positive test result. So out of the, 950 people that had or that are not using drugs, 90 of them tested positive for drugs, okay, which would be 0.0947 or 9.47%, which is not mathematically unlikely, right? So even if you're not using drugs, according to this data, you could still test positive for using drugs, and it wouldn't be considered mathematically unusual for that to happen. Again, at least based on these numbers. Okay, if I could do this last one, or this last one would be good. Okay, this is huge, and we are going to use this a ton for the rest of the course. When we do not use replacement, it's a pain in the butt, because then each time you do one probability, you have to adjust it for the next step. Like again, once we took one person out of the population, then the next time I want to calculate a probability, I've got to adjust all my numbers. What if they said pull 50 people out of there and don't use replacement? Well, then it's going to be a big pain in the butt to kind of keep adjusting my numbers all the way down. We prefer independence. If 2 events are independent, then we just flat out multiply their probabilities together. We don't have to adjust these as we go. Remember, where did it go? When events are independent, right there, the probability of A and B is just probability of A times the probability of B. Okay, I'm looking at my timer. I'm not going to make it. Darn it. I'm going to see if I can fit everything else in one more video, but I might break it up into 2, okay? So let me reset a video.